wall.
When a man applies a force on a wall, the wall offers an equal and opposite force. And the outcome of this interaction is that both the man and the wall are at rest. If the force applied is huge, deformation can happen in the wall and it may fall down. In this example, there are two bodies and two forces in this interaction. The question is, can we have only one force in an interaction? Let us try to imagine such a situation. A boxer tries to land a heavy punch on his opponent. The opponent intelligently sidesteps from the line of action of the punch. The punch goes waste. The boxer could not apply the force in the absence of a resistive force opposing it. From these two examples, we can conclude that forces always occur in pairs and always act on two different bodies. Newton put forth these facts in the form of third law of motion. Newton's third law of motion states that to every action there is always an equal and opposite reaction. Newton's use of day-to-day language in defining this law gave rise to some misconceptions. The two terms, action and reaction, seem like two different things. Actually, both represent the same entity, that is, force. The law gives an impression that action comes first and then its reaction. That is, action is the cause and reaction is its effect. Actually, action and reaction come into existence at the same instant. Action and reaction occur on the same body. Actually, action and reaction forces act on different bodies. Mathematically, Newton's third law of motion can be written as shown. Here, F12 is the force applied by body 1 on body 2, and F21 is the force applied by body 2 on body 1. The minus sign indicates the opposite direction. To avoid all these misconceptions, the Newton's third law of motion can be stated in a simple and clear way. Forces always occur in pairs. Force on a body A by body B is equal and opposite to the force on body B by body A. If two bodies A and B exist within a system, then force of A on B and force of B on A become internal forces of the system, and they cancel each other. Let us observe the recoil of a gun when a bullet is fired. The gun and the bullet are in one system. Initially, the gun and the bullet are at rest, which means the momentum of the system is zero. As soon as the bullet is fired, it moves forward with a very high velocity. Thus, there is a force exerted by the gun on the bullet in the forward direction. According to Newton's third law of motion, the bullet too exerts an equal amount of force on the gun in the reverse direction, which is referred to as the recoil of the gun. If FBG is the force exerted on the bullet by the gun, and FGB is the force exerted on the gun by the bullet, then FBG is equal to minus FGB. If delta T is the short amount of time for which FBG acts, it is the same time during which FGB acts. From Newton's second law of motion, the product of FBG and delta T is the change in momentum delta PB of the bullet. Similarly, the product minus FGB delta T is equal to the change in momentum delta PG of the gun. Initially, the gun and the bullet are at rest. Hence, their initial momenta PIG and PIB are 0. This indicates that the total momentum of the gun and the bullet as a system is 0. As the initial momentum of the gun and the bullet is 0, the change in momentum of the bullet and the gun is equal to their final momentum PFG and PFB respectively. Thus, the forward momentum of the bullet is numerically equal to the backward momentum of the gun, which is taken as negative. As the two momenta are numerically equal but opposite in sign, their algebraic sum is equal to 0. That is, the total momentum of the system is 0. We started with 0 momentum of the system, and its final momentum is also 0. This shows that the total momentum of the system is conserved. That is, it remains unchanged. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. System here refers to a conglomeration of particles or bodies. For an isolated system, there are no external forces acting on it. Let us apply this law to the direct collision between two bodies. Let the initial momentum of A before collision be PA, and the initial momentum of B before collision be PB. When A and B collide, there are two forces created, one on each body, for the same interval of time delta T. FAB is the force on A by B, and FBA is the force on B by A. These two forces are equal in magnitude but opposite in direction. Now, the final momentum of A after collision is P-A, and the final momentum of B after collision is P-B. Applying Newton's second law of motion to the two bodies, we get FAB delta T is equal to P-A minus PA, and FBA delta T is equal to P-B minus PB. Applying Newton's third law of motion, we get FBA is equal to minus FAB. Substituting the values from equations 1 and 2 in equation 3 and resolving, we get PA plus PB is equal to P-A plus P-B. This shows that the total momentum before the collision is equal to the total momentum after the collision. This proves that the law of conservation of momentum holds true for all isolated systems. Now let us look at the equilibrium of a particle. When the net external force acting on a particle is 0, the particle is said to be in equilibrium. Applying the Newton's first law of motion to this situation, we can say that the particle is either at rest or in uniform motion. When the particle is at rest, we say that the particle is in static equilibrium. And when the body has uniform motion, we say that the particle is in dynamic equilibrium. Let us check out the equilibrium of a particle with multiple forces acting on it. When two forces act on a particle and keep it in equilibrium. Then, both forces must be equal in magnitude but opposite in direction. And the two forces must be collinear. That is, the line of action of the two forces must be same. Now let's consider a particle in equilibrium with three forces acting on it. Here, the three forces must be coplanar, that is, they should all lie in one plane. The resultant of any two forces is equal to, but opposite to, the third force. The third force, which is opposite in direction to the resultant and whose magnitude is equal to that of the resultant, is called the equilibrant force. The vector sum of the three forces must be equal to 0. When n number of forces act on a particle and keep it in equilibrium, the vector sum of the n forces must be equal to 0. The vector sum can also be determined making use of the three components of the forces. Sigma F is equal to 0. Sigma Fx is equal to 0. Sigma Fy is equal to 0. Sigma Fz is equal to 0. Common forces in mechanics are gravitational force, which is the weight of a body, contact forces between moving pairs of links in a machine, tension in cables, and tension or compression due to elongation or compression in springs. In this module, we will focus on contact forces. An example of a contact force is the force between a box and the table on which it is placed. The contact force between the box and the surface of the table can be resolved into two components. One along the normal to the surface in contact, and the other parallel to the surface. The component perpendicular to the surface is called normal reaction, and the force parallel to the surface is called friction. Let us conduct a simple experiment to formulate an empirical relationship between normal reaction and frictional force. Place a cuboidal-shaped wooden block weighing 100 Newton on the wooden table top. The weight of the block will be acting vertically downward and will press the tabletop down. The tabletop will press the block up with a force equal to the weight of the block. The upward force of the tabletop on the wooden block is known as normal reaction. Let us now try to slide the wooden block by pulling the spring balance attached to the block. As we slowly pull harder on the spring balance, the friction force automatically increases and becomes equal to the applied pulling force. This automatic increase of the frictional force takes place up to a limit only. The frictional force at this point is known as limiting frictional force. At this point, the applied pulling force is equal to the limiting static frictional force. The block is at the point of impending motion. That is, the block is on the verge of moving but is not actually moving. We can repeat the experiment by placing the wooden block in different positions, such that different surfaces are in contact with the tabletop. We will find that the limiting frictional force is same in all cases. If we repeat the experiment by using a stone and an iron block in place of a wooden block, we will find that the limiting frictional force is different in all cases. Limiting friction increases as the mass of the block increases. we find that the limiting frictional force is independent of the contact area between the two surfaces. When the block actually starts moving, the frictional force experienced by the block is known as the kinetic friction force. The kinetic frictional force is always slightly less than the static limiting frictional force. From the results of this experiment, we can arrive at an empirical relationship between normal reaction and limiting frictional force. These empirical relationships are also known as the laws of friction. They are: static limiting friction is independent of area of contact. Static friction is proportional to normal reaction. It is equal to the product of mu s and n, where mu s is the coefficient of static friction. Kinetic friction is proportional to normal reaction. It is equal to the product of mu k and n, where mu k is the coefficient of kinetic friction. If the force F applied on the block is greater than the friction Fk, then the net force on the block is F minus Fk, and the acceleration A of the block is the ratio of the net force on the block to its mass. If F is equal to Fk, then the net force is 0, and hence the block moves with uniform velocity. If F is less than Fk, then the net force is negative, and it leads to retardation of the block.